This is another installment of your 2015 Q2 accreditation training. My name is Matt Cowger, and this is a presentation about treating infrastructure as code, prepared by myself and Jonas Roslin. Let's get started. So why would we define, how do we define infrastructure to begin with? What are we including when I say defining infrastructure as code? So we're including the traditional things like the storage and the network and the compute, the things that you would find, for example, in a vSpecs or in a vBlock. But we also include things like the operating system. We include the support services like the DNS or DHCP. And we include things like the database itself. Lastly, we also include the application code itself, any sort of queuing mechanisms it needs or business logic that's involved, some sort of middleware or something along those lines. But why do we define the infrastructure as code itself? It's because we can deploy and connect all of the pieces that we need to run the services for the organization, and we can use processes and tools that make it faster to deliver this and deliver it in a quality way. And the last part sort of comes as a built-in. We get some automation once we do this, which is really convenient. So how do we do it? We store the desired state of our environment in text files. We don't define necessarily how to get there. We decide where we want to be, and we define our target state. We do it in an autonomic way, and by defining this target state so that we can self-correct to a desired state. And that state should be known through monitoring. We should be constantly looking at our systems and our infrastructure and deciding, is the current state the same as what we're looking for it to be? And the last thing we do is we remove what we call snowflake servers, a server that is different than all others. Servers should be as alike as possible, and we should know that, for example, an app server always contains the following kernel, the following version of the operating system, the following binaries, and so forth. So why do we store them in text files, though? Why not something like XML or something along those lines? We do that because it's easy to read and it's easy to edit. Right? If you can read it without spending a lot of time trying to use some sort of tool or something along those lines, it makes it more shareable. It makes it something that I can just send to a colleague or a friend. And even more importantly, it becomes easy to use in some sort of version control system like Git or GitHub or Subversion or any of those kinds of tools. Once we can treat them as text files, we can do versioning on those files and see, hey, when exactly did we move to Ubuntu version 14.04 instead of version 14.01 for this application? Is that the same day that we started having these performance problems? With all of that, by storing the desired state in a text file, we also end up with something that is effectively documentation for our environment that is fully executable, meaning that we can guarantee that the documentation is never out of date from the actual implementation, because they are one and the same. Now, there's some downsides to doing it this way, which is that you end up needing to have people that can read these files. Now, fortunately, these files are fairly easy to read and edit, but it does mean that your people need a specific set of skills. Let's take a look at a relatively simple example. What we're defining here is actually pretty simple. We're defining an Apache web server, and we're saying that the name of the node is www2. There might be another one called www1. And it follows the Apache module, meaning that what I want to define here is Apache, the web server. And we further define that this web server has to have a definition listening on port 80 with a document root at var www.html for the awesomewebsite.com domain. Now, it is the job of this tool, this happens to be for Puppet, it is the job of this tool to go make this true. We don't tell Puppet what files to write or where to insert this in the file. It just needs to make sure that this is what it looks like. And this is really nice because if we ever break it or make a change or somebody does something they're not supposed to, we can go back and fix it trivially. Another example would be to change the root password. Ensure that the user root exists and that its password is the following password. So how does this look as we go. Step one is that the node that we're configuring, whether that's a database server or a network switch or something along those lines, sends some normalized data about itself to the master. And this is a demonstration of how Puppet works, but many of the other systems work similarly. Send some normalized data about itself to the node. This includes things like its operating system, how long it's been up, some of the information about its hardware, that sort of thing. Puppet then takes this normalized data, which we call facts, to compile a catalog that specifies how the node should be configured. Okay? And we actually send that information off to that node. Okay? We say, you need to make yourself look like this. And then the node reports back to Puppet indicating that the configuration is complete and we're good to go. The node has now completed its self-configuration. And this really fits well with the whole software development lifecycle, where we have a constant loop going through implementation, testing, requirement analysis, and design. The reason we do this is because manually configured environments are like a house of cards in a china shop. They are unbelievably fragile. I'm sure that every one of you has had the scenario where you changed what you thought was some sort of minor service password that you thought couldn't possibly be an issue, and everything came crashing down around you. This is true. This happens everywhere. I can say that. I can give that sort of example story because I know that it's happened to every one of you. This is incredibly common, and this is why we try to treat infrastructure as code, because we want to get rid of this kind of scenario. Snowflake servers, these servers where something is special about them, add a ton of pain in deploying and provisioning because we can't do it automatically if everything is unique. And it also adds that friction between someone who's requesting it and somebody who's deploying it. If every server has to have these list of 20 things customized about it, it takes longer. And guess what? Mistakes happen because we're all human. We always make mistakes. And that means that Snowflake servers end up as mistakes. And so what happens if you don't treat your infrastructure as code? Some places have found that up to 60% of failures are caused by human error and not hardware failure. In fact, when I was at a startup that you probably use every day, we found that we had incredibly resilient hardware systems. We used EMC vMax, we used Oracle RAC, we used very high-end servers with dual power supplies and everything like that. We found that we didn't have hardware failures that often. In fact, we found that well over 80% of our failures were caused by human error. And the more we could take humans out of the process of doing repeated things like installing servers, that the lower our failure rate got. Let's take a specific example. There's a company called the Knight Capital Group, and they're one of those companies that's doing, high-speed trading and things like that. And this is a graph of their stock price on August 1st of a few years ago. So what happened? They were manually deploying some new trading software. And they had 8 servers running this software, but they did it in a manual way. And so they put this software on 8 servers, but they didn't fix one of the settings on one of those 8 servers. And so an old function still stayed alive on that 8th server. And it did the trades the wrong way. It did them in a different way than the other 7 servers that were done properly. In 45 minutes, because of those bad trades, they lost